Okay, shocker du jour, home of the shocker du jour. This just came across my desk. Ball lightning caught on film after storm in Canada. You see that? I have to account for this in order to validate my dipole electron flood theory, and I think I might be able to. Now don't forget, this was after a storm. That's one thing. We have to find out what kind of a storm are we talking about. And it's a rare weather mystery they caught on camera, which is ball lightning. Now I studied this a while back, and it does appear to be a completely valid situation, and it is condensed light wrapped around with dark matter. Usually it's dark matter wrapped around with the light. Now we're going to look in space, because I think there's some of this stuff floating around in the ionosphere as well, which accounts for the dark matter that's out there, although there's other possibilities. But I was just studying that too. Looking back to the 1996, there was events captured that they call it the smoking gun. I don't know about that, but we're certainly going to look at it. Okay, this is fabulous footage. Look how far away that thing is. They caught this on video. Listen to this now. This is from a radio station, a TV station, Global News. All right, here it goes.
What is it? It's going for a long time.
A ball of light hovers over a field.
It's like a fireball, but not really. It's the wrong color.
And this couple from Rich Valley, Alberta, was mesmerized.
After a rather vicious lightning strike.
All right, remember that. A lightning strike. This was a storm, a lightning strike. A lightning is that white matter. Now let's continue on.
We saw the ball of fire kind of retain, 20 feet above the ground.
The cell phone.
Okay, 20 feet above the ground. Very important clue.
Video was captured an hour northwest of Edmonton by Ed and Melinda Party. It shows the ball of light for about 20 seconds before it disintegrates. They were under a tornado watch and experienced...
All right, did you see the disintegration? Let's look at that and slow it down a little bit. Now, let's... Did you see that? No, let me just... Okay. You should go in there real slow motion and you get that kind of stuff. Now, let's look at the whole thing under slow motion. See if we can see anything at all. Because it really does make a big difference. So they're looking out and they see this blast of lightning, they said. Now, 20 seconds, that is a long time. All right, so they're looking out and they're seeing this. And she's saying, what is that? And he homes in on her, or she does, whoever. And now I'm going to probably stop it here and there. I'm going to stop it right there. That is an absolutely flawless ball. Now it's radiating down here to some degree. And what normally should happen is the Earth should absorb that energy, because the Earth is basically dark matter. Anything that has substance, anything that has a material substance to it, has a lot of dark matter. And that's why lightning goes right to ground. If you have a charge on you, static discharge, and you touch a water pipe, bang, right into the ground. Here, that lightning bolt has filled the ground with so much energy that this can't get to the ground. It's just hovering in space. And you can see, is this radiating that glow down, or is that glow pushing that ball back up? And I say at this point, that glow is pushing the ball back up. Let's consider this closely. Now, as a matter of fact, let me chime right in on there very closely. Not that closely. Let's go with about that right there. Now, let's continue on with this. And again, it's going to go slow motion. We're watching it. What does it do? Look at it, it's puffing way up. It's puffing way down. Now it's getting smaller. Now it's just glowing very brightly. Blue is a bright glow. And it is going to vaporize right now. I just stopped it. Now let's watch it vaporize. Click at a time. See it? Now watch this. That is discharging out and away from the main body. All right, let's keep going. There's a glow all the way around here. Oops, if you look very carefully. Look at it starting to glow. And it's going to blink out, I think. Now, I can see that down here is gone. Where it had a whole batch of electrons in there that were not being absorbed by the Earth, is my opinion. Holding that at bay, and now that is gone down there. I think you can see that. And now it should vaporize. See it now, it's just starting to collapse. Blinking right on. Go on. Now remember, it started way back here as a glow with a very bright glow underneath. To me, it's a bright glow. You see that? That glow underneath? Normally you would think, well, that's glowing and radiating downward and making this glow. I don't think so. I think these same particles have been absorbed so deep, so many in here, it can't take anymore. So it's pushing backwards. Now let's look way out where I might be able to show that there's some evidence to support that. All right. Let's look at this now. We have the excessive amount of energy in the ground pushing back up, I believe, and it will eventually bleed into the ground, but it's got to absorb it basically. Now let's see if there's still going to be a bright glow. Whoops. All right, I think this shot here supports my statement, because you see that white is gone basically now, or almost gone. So it's not like radiating. It's very, very brilliant, but it will just dissipate quickly now. I'm going to go, and it's very, very slow motion. Boop, it goes away because the resistance to it is no longer there. So it sort of just pops. That's all I can take away from that. I'm trying to understand ball lightning, okay? All I can tell you is I understand the nature of the particles radiating out is raw energy. It's just exactly like the dipole electrons that I show. The white part is that raw energy. And it's all by itself here. Way too coincidental to be a coincidence. You are going to see atomic vapor. All that's coming off of here is going to be the white particles. Now, I don't know how they're doing this, but this is Kugelger Blitz Ball Lightning Con Papier Duchikerdin. I have no idea how to say any of that stuff, so that's the best I can do. Now, what is going to happen? Keep your eye on this. You know what? I'm going to slow this one down too, because it's only 44 seconds, so I'm slowing it down to 25%. Here it goes. I have to turn the sound off, whether it has any, I don't know. So now, look at what happens here. There's an electroplate here. Somehow they're keeping the white particles just vaporizing off. And you can see, I'm running it at very slow motion, but these are just a cloud of vaporizing electrons. I'm just going to watch. It's just like a little smoke coming off there. You see it? Watch it. I shouldn't have slowed it down because it's going fast as it is. You know what? There's no need to slow that down. Let me just go back to full speed. And we'll start over. Sorry, my friends. Here it goes. Full speed. That is electronic vapor. That is atomic vapor. Those are just the white particles in basically a foam rising away. Just like they go from the sun. They vaporize out into space. Well, this is vaporizing into a positive plate, just pulling all these negative electrons in. You see that? It's just pulling those negative electrons in. How they did this, I don't know. And it's in German or whatever it is. Looks like German to me. So I really don't know, but I can tell you what. That is exactly what I predict in dipole electron flood theory. That is atomic vapor. All right, watch this. This goes back 7 years ago. I did something, I called it very rare ball lightning in Russia. And this is all somewhere in Russia between these railroad tracks, and which makes sense to me in a sort of roundabout way, because that's where the field would sort of surround that. And watch what happens to this ball. All right, I'm pointing it out. I don't have any sound on, but I'm pointing it out. Now, what will happen is they're going to go and they're driving down, and this thing is going to try to catch up to it. Watch. Here it goes, watch this. It's coming down this way, and the thing will come up and up and up like that. Look at it, zoom right up to him. All right, this was ball lightning, and it was in between the railroad tracks, and I can sort of understand that to some degree. Now, is this some kind of electric trains? I don't know. I see these big poles here. What's that about? I don't know. There's things to take into consideration, but that is a very strong glow riding those tracks. Now, I'm showing this was 7 years ago, a video I did, so here it goes. Watch what happens. It's going to come bouncing back and forth, like almost catching up to the train. It wants to be attached. Look at it, zoom right up. And then for some reason, oh, watch, right at those poles. This is when it's slowed down. Wow, I didn't see that. All right, it bounced back. Here it comes. It comes right up. Boom! It hit that pole, or at that. There might have been. Well, this time it didn't slow down. Well, maybe it did. Wow, this is just starting to make sense to me. The trains in Russia, where this was, I think this was, run on electricity. This is ball lightning that is in this area here. Now I'm going to play this. Let me shut the sound off. Now that ball lightning just starts to glow between the railroad tracks, just like I showed you before, the one that was trying to catch up to the train. Now, it's not moving right now. I have it shut down. I'm just pointing, saying something. I forget what I'm saying there, but it doesn't matter. This is going to start to move, and then it's going to discharge through a. Hold on one second. This is a video I did years ago, and I put down the mystery of ball lightning, extraterrestrial, natural, the great misunderstanding. Nobody understands ball lightning. Now, this is, I believe, electric train area, and this is ball lightning. This is just solid energy. Now, how they energize, do they energize the tracks? I don't know what they're doing here, but I do know, as you will see, what's going on. Let's watch this, and I'll try to explain it, and I will stop it when it's appropriate. But right now, it's glowing, and it's going to move a little bit. You see? Oop. Let me back that off just a hair. You know what? I'm going to slow this down to 25% because it's only going to take a second or two to play it. So we're going to go to 25% now. Let's go back to where it was here, and it's starting to glow. You see my finger pointing to where the start of the glow is? It's trying to find a place to discharge to, basically. And for some reason, this area is pushing back, and it's going to discharge. Watch. Keep your eye on there. All that white stuff is going to discharge over to there. So it's setting up shop, getting ready to do its discharge. %, runs really slow. Okay, this took forever to get to this point, but that glow that we saw before discharged right to that spot there. There was a little glow started here. There was no conduction between these 2 points. Little tiny glow was here, and then all of a sudden, it came across, and now it's still looking for a place to discharge to, and I don't think these things are letting it discharge. So it goes up to a lamp post. You see back here? You remember back here? Whoops. Hold on. All right, you remember how glowy it was here. Well, we just saw it discharge over to here, and then there's a little white spot that goes for a time being, and then there's a little tiny white spot that shows up there just for a second or two, and then it discharges. My finger's pointing to where it will be. All right, there's a little tiny white spot shows up here, and then that jumps to the white spot. Then it jumps from there up to a, I think it was a street light. Like I said, this goes back a pretty good number of years. It will jump from there to here, and then jump here, and then I believe it jumps up to the light pole. Any second now that should be jumping. There it starts. Now it's starting, and it's going to come across and interact with the other metal pieces, but it still can't absorb it. To me, the metal should absorb the electrons. Now, is there some field set up that says, no, I push electrons away, and that's what these, see it? Getting ready to jump over. There's got to be something that says, I push you away, you white particles. So it sort of bounces, see it, there it goes. It bounces across, and it still can't discharge. It still can't slide itself into that metal. The metal says stay away, and that must be the way they polarize the tracks to keep the trains almost levitated, I think. Maybe, I don't know, I'm just guessing. All right, so now it jumps over from there over to here, And now it's collected on here, and it still can't absorb it. So it moves from there over to here. At such a point, right here, it can't discharge until it sees a good ground. Even though it's above, it's a good ground. Watch what happens. And it explodes that light fixture. I'm pointing to it there in extremely slow motion. Now the light fixture has a ground. That white stuff wants to hit something and go deep down into the ground to be absorbed. And it finally says, I am going to jump up to that thing because that's the only place I can find that will take me as a bunch of electrons and let me go to ground. So it goes up and explodes the light fixture, if we ever get to that point. All right, I'm showing it here slow motion here. Let me just move up here. All right, there it goes. You see that? Right there. Finally it says, that's it, I'm done. Zip, straight up. Straight out of there. All that's just nothing but a stream and a bolt of lightning, basically, just going upwards, because it's looking for a ground, and now it's going to go down through that ground. All right, so it shoots its way straight up through there, and it will come down through that ground. I'm showing it over again, I guess. And then I show all this stuff about the strange shapes and so forth. That's interesting. Magnetic separator. Now, then I show all of our light particles and stuff. All the stuff I did with the light. Rod Warren and I. And it went on and on and on about the dipole electron flood theory. And like I say, this goes back quite a ways. I still had Caesar. Caesar was here, see? Caesar was here. Anyway, that's it. And I start bragging about understanding the, dipole electron flood theory. You have to. These are the only stable ones. When you take this, whoops, let me back that up. Just, only take a second. Very simple. This is carbon. All right. Now carbon is right there. It can decay down to boron, or it can decay up to nitrogen. Here's where it's stable. If I take a couple of them away, it will go down to boron, even beryllium, all right, which is lower than boron. You take some more away, it goes to beryllium. That's what isotopes are. These are isotopes of carbon. Carbon is 6, but it can be huge particles, way different than 6. So we take a few away from the stable state, it goes up. It goes down almost towards the hydrogen, let's put it that way. If you add extra ones, it goes up towards nitrogen. Very simple. But you have to have all these particles to do it. You can't do it with a couple of protons and a couple of neutrons. It doesn't work. These isotopes could never work. They just don't happen when you take into account only the size of neutrons and protons and mix them. You cannot get these isotope values. It just does not happen. Impossible. You have to have these many particles. And then the enzymes come in and they go, and they bring it this way or they bring it that way. They can go both directions. That's how the heavy metals are made, is by isotopes and by enzymes. and half-lives. That's how they're made. They're not made from the Big Bang. And a lot of things that are just not right and need to be spoken about, and I want to have a voice in that conversation. I've done this all my life. I understand this very well. And this is dipole electron flood theory, and energy flows from light to atomic vapor. And I think I might have shown you this, but I'm going to show it to you again. They just proved it again today. They went through the solar corona, and you can see it's just like burning a house down just prior to the nuclear bomb knocking it over. Watch this. Okay, I'm going to show you the most exotic particle ever seen, ever. This is what they show as the Higgs fields from Fermilab. This is their picture. Now, that's obviously just a drawing. Now, we actually have the Higgs fields, and they are circular like that, only we didn't use huge particles and smash them to bits and see all kinds of different debris flying. We used tiny particles, and they came out like this and made these elegant looking fields. And that's because the white particle had separated completely from the black. Just completely white. Now, the black is trying to dig in. And when it does, it creates the fields. Those fields are a product of the black interacting with, the white interacting with the black. This is on this side of the Venturi. The light has come through here. Now, you see this one? This is about the best shot I can give you. There's that white particle, and it's starting to grab into some black. And apparently, all I can say is, at this point, I believe it hits the outer rim and starts to create a circular pattern. Why, I'm not 100% sure, but I believe this is the energetic race. And it creates an inward field. Why, I don't know. But like, again, you see how energetic that race is out there? And then it's pushing inwards, creating like a substance almost. That's all I can say. It's like a substance, and it's bouncy. And when red is just kind of bouncy, and then green is a little bouncier, and blue is pew. But I believe that's where it starts spinning. Now, that brings up the point of these are being Higgs fields. Now you can see they're all red because it was red laser. However, what about this one? That one's being crushed sideways, and it's turning it purple. And I got better shots of this. And then I have a shot of a particle. I don't think anybody's ever seen one like it. And I have only seen one, and I have seen more particles than CERN has. That I can guarantee you. I worked on these kind of pictures daily, and I'm talking a lot of them, for years. Don't forget, that's the light, and it's just now popping back into particles, which they call Higgs fields. So it's not that the Higgs fields, they have it backwards. The light, when it reattaches to the black, it creates the Higgs fields. It's not when the Higgs fields break apart, they create these particles. And I think that's what they believe. I think they have it backwards. All right, they say these Higgs fields give mass to particles. Well, you might be able to put it in that respect, because there is no mass to the white part, none. So I could say they give mass. I'll go along with that. But, well, let's just go with that. They do give mass. I'll give them that. I agree. All right, so don't forget, we were looking into here, and these fields, just like this, are showing up right in here and showering out at us. And that picture was taken in as the fields come out this way. And they go in the same way they come out. These are the kind of fields that are going in through the Venturi, and they come back out again when they come out the other side, as I just showed you. Don't forget, you see this fields, the way they're curved like this? And the only reason you see these is because of the push back. They're over here. They're coming along just like this one. This one you see because it's accelerated forward. These see because they're being pushed back by the explosion of this interaction here, which is off the charts explosive energetic. It way back here, electromagnetic force, just, and then the particles just keep going this way. The black separates from the white, and this is the interaction right here. So don't forget, coming out there is this. We see this hitting, making all these fields. Looking straight into this is looking sideways at this coming out. Looking like down this way. Seeing this. This is like looking straight into the Venturi. Now I want to show you something. It's, like I say, I've seen a lot of this, and that is the only time I've seen this. And what have I seen? What's the only time I've seen? And what is it that I've seen the only time? That right there. That right there. That little white dot. You see it? It curves like this, and you got that white dot. Now we're looking right into the Venturi. It's coming at us, and these Higgs fields are interacting with the dark particles. They have to be just waiting for them to come back out at them, and they're combining back with the white particles, turning into regular photons again. All right, so when they came through here, they came out as just pure white. You see them? Pure white. Pure white. You see that? And then they hit the dark particles, and they turned into little fields, spinning fields. And you can see the little dots in here. Now, it's almost like they're pushing against themselves somehow, and this is the actual particle spinning around. I don't know how to explain it. I really don't. But that is the one that we're going to focus. Whoops, you can't see that. That one right there, that white one, is the one we're going to talk about in a minute. I've never seen another one like this. That, I believe, is a reverse spinning particle, and I'm going to show it to you what happens when it decays. Okay, we need a physicist here to tell me what they think has happened. That's that little white particle. I'm almost 100% sure. I'm not 100% sure. I believe it is. It came in a separate photo of the same batch, and I've never seen a white one like that before. And Rod spent so much time, he must have just continued to work on that until he had this. He must have spent thousands and thousands and thousands of hours. And I did probably too by the time I was done analyzing. This took me 3 years to figure this out. Now, I'd like to have a physicist tell me what they think. You see that little white particle? You see this field here? And you see that? That's not a Higgs field. What is it? What is that little, I call it a mini disk. It's a little trumpet. You see it? What's going on, and what caused it, and why it caused this. And is it that particle? I believe it is. I got a lot of information about this, and the black can completely push the white in front if it's set up correctly at the Venturi, to where it funnels it down just enough black and the white so that the black is the pusher of the white. They separate quite easily. It shocked me when I found out they could separate like that just so easily. And they knew this. This is from Fermilab. These are the two particles they found. 2013, same time we did. I got a hold of them. I showed them my stuff. I said, we found the same particles you found. Here they are. There's your particles. Here's our particles. The same thing. And they do the same thing. This has all the energy. They get big and small. This never changes. It's a sterile muon. Has a glowy edge. Same thing as they said at CERN and Fermilab. And this is light. These are photons. These are where they want to get down to, is the smallest particle, and use that as white light right there. That's what they should be wanting to get down to, is right here, and harvest that right there. And you could put dozens and dozens of these, hundreds, thousands of them in a little shoebox. And I think that it's supposed to create a minimum of 200 times more energy here than you started with there, if you can separate the white from the black, which we obviously did. That's what I was told. It may be much higher than that, because I just saw some things from CERN that show that the increase in energy is basically exponential. Okay, here it is right there. This is from CERN, I believe. And this is the laser coming in through the venturi, creating high energy electron showers, high energy electron showers, low energy coming through the venturi before it showers. Low energy showers, high energy showers. So they're high here, they were low here. We increased their energy. What happens to the muons? These are the electrons. See, electron? These are the muons, the black balls. They come up, bang, and bounce back. The white goes through and creates the showers. Well, what does that mean? What does it mean right here? It means if we could harvest that and run it down into a bag, to wherever you want, you could use it or you could store it. And you use a little piece of it to come back to keep the laser going, and you got free energy. You could carry it around in a little lunchbox. And don't forget, high energy showers. Well, how much is high energy? How high is high energy? So if we had an electron shower, what would it do to energy? All right, you see this? This is potential energy. It means it's energy of an object possesses, due to its position, shape, condition, has the potential to be converted into other forms of energy. It could be a gigantic ball dropped off of a cliff. In this case, it's not. All right, in this case, we have stored energy because of an excess of electrons. Well, how much of that? Hold on. All right, potential energy just means energy that can be used. It's just energy that is waiting to be used. You can use it right away and make a kinetic energy, or you can keep it stored in a battery. It says in physics, the symbol U typically represents potential energy. It denotes potential energy in the various contexts of any kind of energy, but the U is the potential energy. Now, you can turn it immediately into usable energy, which is kinetic energy, or you can store it in a battery or whatever, or you can take it to wind up a big heavy weight, and then a big heavy weight will come back and unwind itself. All right, so there's all kinds of ways to store and use energy. It's not just electricity. However, in this case, it is. All right, so as I said, inside this box, these little tiny devices are the size smaller than that. You could have literally thousands of them in here, radiating out laser, collecting it on the other side, just the white part, let the black part go away. And you may have to do something. I don't know. That might require a little bit of engineering, because there's going to be so much dark matter collecting inside and the white spitting out. I don't know. I really don't know what that's something that it might have to be engineered. But I can tell you what, we are accelerating that light, and we are creating these high energy electron showers, electrons, and we are backing off the muons. They back out. That means this should have enormous amounts of energy, because once you hit this particular spot, let me show you what the data visualization of the energy is. This is of the showers, the particles. How many electrons? Here you just got a few, and then they shower. And you create just huge scattering amounts. The muons, they come in and they just bounce back off. This is what we want to collect, and this is where we want to collect it. All right, so here we are going through the accelerator. All right, so we're coming down this way. We're coming down this way. These are the two separate things. Remember, I talked about the U. It's potential energy. It's energy. It doesn't matter if you're using it right now. It is the capability to do work. That's what energy is, the capability to do work. However you do it, doesn't matter. In this case, it's electricity, but it makes energy, the capability to do work. It's starting down here at almost zero. We have almost no energy whatsoever when that laser starts to come in. When it hits the Venturi, this is 3,000 times what it is down here. And this is where it started in. And then it started to build up a little bit, and then it started to get pretty serious, and then right through the roof. This is the particles. This is the number of the particles of showers. All right? These are the electrons. See the E? The U means the energy, and that's right off the charts. And the electrons means the number of electrons. So here you got, you know, it's building up. This is the number going up this way. So coming in, it's just some electrons, and they keep banging and banging and banging and banging and banging. So they're pushing more and more and more as they go forward. And then just before they hit the Venturi, it looks like they drop right down, which could be. And then they're sucked through the Venturi. This probably is the Venturi. And out the other side, they go right up like a rocket ship, because that's the spray. It's exactly what I found. Exactly identical. No difference whatsoever. And I don't see why we can't get that kind of energy. And the only reason it's safe and is that these reattach almost instantly. Those showers of particles, just like that, they're back together with the black ones. The black ones just have to be roaming around waiting for white ones to come along to attach to. That's all I can tell you. That's as far as I can figure it out now. All right, I just showed you the graphs. Now I'm going to just explain them one more time. I showed you this is the particles coming down. These are the electrons. They're attached to the dark matter, yes, which is the muons. So the electron goes into a shower mode. Right about here, it starts to gain energy. Remember, the graph comes in, well, it came in from this way, that way. But let's just turn it around, and we're coming this direction. So it's just barely got any energy, almost nothing. The only reason you even see this is because it's being accelerated that way, gaining energy. As it gains, all of a sudden here, you're starting to see that bump come up. And then right here, it drops down to nothing as it goes through the Venturi and then splashes everywhere. That's the white. The black stays back, which is the muons. The black stays back here. The white comes through here. Now it rejoins with the black instantaneously. This is the, you know, I mean, it's like this, I don't know, it's very, very, very close. Don't forget, we're working with light. Light has a good sized field. It's not just a tiny little field. When you energize light, you can get a really serious field. Well, you know, when I say serious, it's a lot more than just like the pinhead. It could be maybe that wide, maybe even bigger. It's hard to say. It depends on probably the intensity of the impact, but it's going to be the same particle. All right, so don't forget, this is us. These are our actual experiments. That's actually a red pulse laser with CMOS from a smartphone taking these pictures back in about 2013. This phone was from 2012, Galaxy S3, Samsung. And that's what did this with a bar. Well, hold on one second. I got it here. Oh. This is exactly what took this. A Bosch GLM15 pulse red laser. And you wouldn't even see that. You don't see that when it's shining through. You don't see that. And this is the phone that took the pictures. Galaxy S3 from 2012. And this I had a little bit of a discussion with Fermilab and CERN, and University of Geneva about that we could see this with CMOS. And eventually they acquiesced and said, yes, I guess you're right. And the only reason we could see it was because we weren't working with protons. We were working with the electrons, so it didn't damage our CMOS. They're made to pick up these particles, no matter how powerful they are. But they do not work well when you hit them with something like that with extreme power. It's all over. It destroys the CMOS. So we were okay. What they had to do at CERN, and they are doing it right now, they're upgrading to make radiation hardened CMOS. They want to smash big things. I don't know why, because the big things are only made out of these. They're only made, every one of the littlest particles is a dipole, which means a positive, negative. It's basically a little tiny magnet. And at a certain quantity, they bond together to form a unit, which we call a proton or a neutron. It's right there, 1839, 1840, something like that. Now, that's what we're looking at right there is an energy increase that's staggering. And again, that is not my doodle right here. This I did not do. But I can read. And it says energy goes off the charts, as does the shower of electrons. All right, quite easy to see what they're saying right there. Now, I don't see why we can't harvest that energy. I just can't imagine why nobody will talk to me about this. It's been over 10 years, and they knew these are the same particles. They're the same particles they found at CERN and Fermilab. This is Fermilab's particles. We found the same exact ones. They have the same characteristics, the same weights, the same glowy edges, the same puffy, and just a field. And you know, space is packed with empty space isn't empty. This is 2013, and you know, like I say, I'm not a quiet guy, and I tried to work with Fermilab, and it did not go well. And it still hasn't gone well, and we're the ones that could have maybe had some energy. And I'm telling you, the Earth is in terrible, terrible problems. And these are the particles from Fermilab, and these are our particles. And like I say, I ended up going to the University of Geneva for particle physics through Coursera. I engaged with the professors. They agreed eventually that this could be done using CMOS. And now you see them saying, yes, you can see electrons and muons and so forth, cosmic waves, cosmic radiation, all that stuff with a smartphone. Because you can very easily. And more than that, you can see all the magnetic fields in space. You just have to have the right settings, I guess. I didn't do this. This stuff gets sent to me. And this is not AI. This was years ago. This was another one. Got a new cell phone. Someone else took some pictures, and this is it. And these are all dipoles. And this stuff has got to be on this side of the moon or on the surface of the moon. And all these things here, what is going on here? I have no clue. I look for the dipoles, I look for the magnetic fields, and you can see them on steroids. Look at that sucker. And I think I know what this is, and it's got a double magnetic field. All right, somebody figured that one out. And then also tell me about these dipoles and about this blue hue, and all of these dipoles and these magnetic fields. And then go back to this one more time and take a look at this one and see the same sort of evidence. And all of these fields interact with all these other fields. And everything basically is a dipole. If you get close enough and look, you'll see that's a dipole. These are dipoles. Sometimes they're a little pixelated. You really can't tell that well. But sometimes they make the weirdest looking dipoles. And that is also what is predicted in dipole electron flood theory. The white part can get enormous. The black part never changes. The black part never changes. This is probably pretty close to us because we can see the black is pretty big compared to the white. And you'll see them getting bigger and smaller as they go further and further away. And with the app, you may see some distortion, absolutely. I don't know anything about this. All I know is he took this with a cell phone. I get so much stuff from so many people. And here's the blue going so fast, coming in. is spinning to the right, which would cause the particle to drift to the left, because this is one shot of that particle all in one set of little pixels. And actually it's just the particle in one little clip of how it's moving. It's moving that fast, and the picture is, and you can see, you can't even tell it's two particles here, which is two dipoles, but by the time it gets out here, it's slowed down enough you can see it. So we know that light can come in fast and slow down very fast. And we also know that light can come in slow and accelerate very fast. And we also know that light is made of dipoles, which are the black and white particles, and they are in photons, and those photons can smash into bits. This is their normal configuration, and that you can't really pull those apart. That's the strong nuclear force. Well, through the Venturi, it just happens that it works on itself, because it slams those white particles. It pushes the white particles and it slams them, and that I can prove too. And it just slaps them, bam, 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 and they're squirting through here with a vengeance, as I will show you right there. There's that black particle wave pushing the white. The white's not just falling through it, the black is pushing it. So at the other tune, when it's tuned in another direction where only you get white, there is no black, that's when you can harvest it. That's when you can put a harvester right here. There is no black. It's just a white. And it's all about the tuning, and they might have something to do with the materials and everything. Like I say, Rod did just a staggering amount of work. Years and years we worked on this. And I think we could get free energy. So I'm going to leave it at that. All right, and like I say, I think I have the evidence to support what I'm saying, and what we know for sure, I don't think we know for sure. I'm sure we don't know for sure what we know. Think we know for sure. I'm pretty sure. Actually, I'm very sure. 100% sure. Anyway, I love you all. What we know for sure? No, we don't know anything for sure at this moment. Everything has to be re-examined. Once you say you know something for sure, you're done. You're not a researcher, you're not a scientist, you're done. You're done. Because you say, oh, no, we know that's for sure, so forget about it. No, don't forget about it. What about this? I have new evidence. The evidence I have is overwhelming and cannot be denied. But we know all these things for sure, so don't pay attention to Roger. Well, no, you don't know these things for sure. You know them now for sure, because I'm showing for sure the particles that they found over 10 years ago, and we did too. All right, so I guess that's enough for now. All right, thank you. Love you all. Bye.